Hey everybody, welcome to the first lecture video for our our Chem 3B Fall 2020 semester. So in this first chapter, we're going to talk very generally about organic chemistry. So we'll just kind of jump right in. Now, organic chemistry is the study of compounds of carbon. So anything that contains carbon is an organic compound. So organic compounds are made up of carbon and a few other elements. Often there's hydrogen, which we represent with an H, oxygen, an O, and nitrogen, an N. Also present in some organic compounds are sulfur, phosphorus, and a halogen. I don't know if you guys remember halogens from Chem 3A, but these are things like fluorine, chlorine, iodine, bromine, and those are the common ones. Now, why is organic chemistry a separate discipline within chemistry? Why do we need to sort of separate special compounds that contain carbon? Because if you remember, your inorganic chemistry, your Chem 3A, didn't cover carbon-containing compounds. And so historically, scientists at one time sort of believed that a vital force was present in living organisms and that was necessary to produce an organic compound. And so for a long time, organic compounds were sort of thought of as only something a living creature could make and not something that we could even study in the lab. So there was not a whole lot of work being done that way. Now, an experiment in 1928 was the first in a series of experiments, actually, that led to the demise of the vital force theory. Now, basically what happened is we were able to, or a scientist was able to synthesize an organic compound. And that compound is here, urea. It's one of the simplest organic compounds. It contains carbon, as you can see. This one has what we would say is two amino groups, these NH2s. So this is also an amine. Urea is an amine. It's got amino groups, and it's an amide. An amide. There's two words that you're going to have to learn, two different functional groups. The differences are going to be amines do not contain carbons double bonded to oxygens, where amides do. But we'll get there. So scientists were able to synthesize an organic compound in the lab. Now, there's a lot of information that we can get from the presence of organic compounds. For example, when we have looked at some comets, and when we have looked at some compounds on Mars, we see that there is potential for life because some of the organic compounds that would be necessary building blocks are present. From urea, we can combine urea molecules together to make bigger compounds that contain carbon. And so it's a nice way of sort of seeing if all the parts are present for life maybe to be there. In the absence of organic compounds, we would probably expect not to find any life. So let's talk about just the sheer number of organic compounds, just to give you an idea. There have been discovered or made about 10 million organic compounds, and an estimated 100,000 are newly synthesized or discovered every year. Now, by comparison, chemists have discovered or made an estimated 1.7 million inorganic compounds. So here we're talking about 10 million organic compounds compared to 1.7 million inorganic compounds. So there is a whole lot more of organic compounds than inorganic. So basically, 85% of all known compounds are organic. So they make a big proportion of the compounds that we want to be interested in. And of course, this class is going to focus on that. Now, there is a link to biochemistry in the sense that there are carbohydrates, lipids, proteins. I never know if I spell proteins right. Enzymes, which we'll say is a subsection of proteins. Nucleic acids. Hormones, vitamins. I'm not going to list them all. Vitamins, and a whole bunch of other chemicals in living systems that are organic compounds. In fact, I have a list of some of these sort of properties that we can compare. But biochemistry then is, of course, very interesting to us because it involves lots of different organic compounds and how they all sort of convert into each other or are related to each other. And this means, understanding metabolism. This means understanding how muscles work and how muscles grow. And of course, we're not going to be able to go into all of those details, but we'll look at some of the basic biochemical structures, of course, all of which are organic, and we'll look at very, very sort of superficially where they're found in the bodies and how they work. Let's do a little comparison between organic compounds and inorganics. So organic compounds, you can see, are covalently bonded. This means that they're sharing electrons. Covalent means sharing. So let's say that, shared electrons. Let's compare that with inorganic compounds. These are compounds that do not have carbon in them. Not to say that they don't have covalent bonds. They do. Sulfur dioxide, for example, is covalently bonded, and it doesn't have carbon. But often, inorganic compounds are going to have ionic bonds. And if you remember K2SO, let's say K2SO3, this portion of the molecule is covalently bonded, yet it still has a charge that's attracting these potassiums. So ionic compounds tend to have charges, but not always. Going back to organic compounds, many are going to be gases, liquids or solids, and they're going to have low melting points. Most inorganic compounds are going to be solids only and have high melting points. Or inorganic compounds are going to be soluble in water because water is very polar, and polar compounds like things with charges on them. And ionic compounds, since they have ionic bonds, and ionic means basically charged, doesn't mean charged, but ionic means that we have charged species like positively charged ions or negatively charged ions. These are going to like water. Organic compounds tend to be insoluble, but they are soluble in organic solvents. And these are, again, solvents are anything that can dissolve, let's say, we can call solvents liquids, but they don't have to be liquids. In a solution, a solvent is just the majority, whatever you have more of. We tend to use water as a solvent for things, but diethyl ether, toluene, hexane, benzene, these would be different kinds of different kinds of solvents that we could use to dissolve, let's say, organic solutes. Because when these things dissolve, they don't have charges, they tend not to conduct electricity, whereas we know aqueous solutions of inorganic compounds, like a salt water solution, this would definitely conduct electricity. Organic compounds are flammable and combustible, and they will basically burn. And inorganic compounds don't tend to burn. Organic compounds have slow reactions. Inorganic compounds react very quickly. Okay, that's a comparison. Let's take a look at some organic structure. So there are structural formulas. Structural formulas show the atoms present in a molecule as well as the bonds that connect them. So what you are seeing here are a bunch of structural formulas. Now, you have to kind of think back to your Chem 3A, to your Lewis dot structures. If you haven't taken Chem 3A in a really long time, you're going to want to go and read up on this and learn how to do it again, because we are going to draw some molecules, or I'm going to ask you at least to predict the shapes around some molecules, which means you're going to have to draw them and then figure out the shape. By shape, I mean the Vesper model, or the Vazquez model, the valence shell electron pair repulsion model, which states that the number of electron groups around a particular atom is going to determine the angle of those atoms, or the bond angles. So if we have something like this, where we have a carbon that has only two electron groups around it, then we're going to see 180 degrees separation between those two, as a bond. This bond will have 180 degrees, it'll be 180 degrees away from this bond. I think that might be how we say it. Or the two atoms that are connected to that carbon will be 180 degrees away from each other. If we have a carbon, such as here, that has only 3 electron groups, then all of our bonds are going to be 120 degrees. And if we have 4 electron groups, we call this tetrahedral, and there is 109.5 degrees. So organic structure depends on a combination of these things. Structural formulas that allow us to look at how the atoms are connected, and the Vazquez model that lets us predict the shapes around these molecules. And this is going to be important so that we can tell if two molecules are the same, if they're different. They might be constitutional isomers, they might be stereoisomers. We'll learn all of these terms down the road. We want to make sure that we want to be able to tell if a molecule is going to be polar or not. And often that has to do with what type of bond angles and what type of atoms we have. Now, I'm getting ahead of myself, so let's continue. So we're talking about organic structure. Now, oh wait, I think I might have more to say about organic structure. Let me go back here real quick. So among the neutral or uncharged organic compounds, I want to show you what kind of bonding structures we tend to see. So for carbon, we have usually 4 covalent bonds. So I'll write that out. So carbon is usually going to have 4 covalent bonds. And you can compare that to what you see down here in any one of these pictures. Carbon with 4 covalent bonds, carbon with 4 covalent bonds, right? 3 here and 1 here. This carbon has 2 covalent bonds, then 1 covalent bond, then 1 covalent bond, for again, a total of 4. Hydrogen, we're going to tend to see with only 1 covalent bond. So we tend to see that guy on the end of molecules. Nitrogen is going to have 3 covalent bonds and a lone pair. So lone pairs, you can see that this chlorine here has 3 lone pairs. This nitrogen right here has 3 covalent bonds and 1 lone pair. Oxygen normally has 2 covalent bonds and 2 lone pairs. This will help when you guys are drawing out structures. So here you can see oxygen with 2 bonds and 2 lone pairs, and same here. 2 covalent bonds, 2 lone pairs. And then halogens typically have 1 covalent bond and 3 lone pairs. So a halogen, 1 covalent, 3 lone pairs. Now, let's see. I'm going to look in your book real quick and see if there's any tips I can give you guys on writing Lewis structures. So let's do a couple just to remind you. So let me show you how to write the Lewis structures for a couple different compounds. Let's do H2O2. Let's do N2H4. No, let's do CH3SH. And we can do one more. How about H2CO3? Okay. So the first thing that you do when you are writing Lewis structures is you total up how many valence electrons you have. Now, if you don't remember how to do that, it comes from the column of the periodic table that they're in. So, for example, hydrogen is in the first column of the periodic table. And so, since there's two hydrogens, we were going to get 2 electrons. And then oxygen is in the 6th column. And it also has to do with how many valence electrons you have. And so, if you remember, column 6A has 6 valence electrons, column 7A. Some periodic tables is actually called column 16. But oxygen has 6 valence electrons, and there's 2 here, so that would be 12. And so 14 electrons total. We next remember our rules. Oxygen wants 2 bonds, 2 lone pairs. Hydrogens only want 1 bond, things like that. So we can arrange our oxygens and our hydrogens into some fashion and then try to put all the electrons in. I like to start with bonding electrons first, and I put my hydrogens on the outside because I know that they can only bond 1 time. 2 electrons, 4 electrons, 6 electrons. Remember, every line represents 2 electrons that are being shared. 6 electrons, 8 electrons, 10 electrons, 12 electrons, 14 electrons. So I've used up all my electrons. And the object here is to give every atom at least 8 electrons, except for hydrogen and helium, which only want 2. So I can go in here and just count that this oxygen has 2, 4, 6, 8 electrons. The hydrogen has 2, and that's all it wants. The other hydrogen would be the same. Now, we could also just actually let's do the Lewis structures first, and then we'll talk about the bond angles and the shapes, because we would classify these by particular geometries. Though I don't know if I'm going to necessarily ask you to know the names of the geometries, but you should know the bond angles at least. Yeah, bond angles and geometries. So I'll have to tell you what those are. Or you'll have to refresh your memory from Chem 3A, but I'm going to show you here in this example. So let's do another one of these. We've got carbon, 4 hydrogens, and a sulfur. So I'm just going to kind of go faster here. Carbon has 4 electrons. The 3 and 4 hydrogens altogether is going to be another 4 electrons, and then sulfur is just like oxygen, 6, so another 14 electrons. I've got a carbon. I'm going to put some hydrogens around it. I know carbon likes to make 4 bonds, and hydrogens only want to make 1. So I'll do something like this. 2, 4, 6, 8, 10, 11, 12, 13, 14. Now, sulfur is just like oxygen, so it's going to have the same bonding trend, 2 lone pair, 2 bonding. But you would also have figured out where to put these remaining electrons if you just think about who needs the electrons. We would have already seen that carbon had 2, 4, 6, 8, so there wouldn't have been any room on any of the carbon atom for those electrons. And we would have also seen that sulfur only had 4 electrons. With the covalent bonds, it was missing 4 electrons. So we would put those lone pairs there. For the last Lewis structure, 2 hydrogens is going to be 2 electrons. Carbon is 4. Oxygen is 6, and there's 3 of them, so 18. So we've got 24 electrons. I'm going to put my carbon in the middle. I'm going to put my O's on the outsides. I'm going to put some H's beyond those. Now, I picked some challenging ones. If you remember doing this with your inorganic compounds in Chem 3A, you probably remember it being a lot easier. Well, that's because they didn't have carbon, and carbon's a tricky guy. So we've got 24 electrons, so 2, 4, 6, 8, 10. Carbon's going to need some more, so 10, let's go 12. Oxygens are missing a bunch, so let's add in some more for the oxygens. 12, 14, 16, 18, 20, 22, 24. Basically completing the octets for everybody. We see that all the oxygens still have 2 bonds and 2 lone pairs. We see that the carbon has 4 bonds, and we see that the hydrogens are on 2 of those O's. And so these would be your Lewis structures. Now, the other thing we could do is predict the bond angles around each well, like, we'd have to pick an atom, so let's just pick atoms at random. Let's pick the bond angle and geometry here, the bond angle and geometry here, and the bond angle and geometry here. So we would look at the O, we'd say how many electron groups? 1, 2, 3, 4. So 4 electron groups is going to be tetrahedral in terms of its electronic geometry. Electronic geometries that are tetrahedral have bond angles of 109.5. Now, what we call this particular geometry of 2 lone pairs and 2 bonding pairs is bent. So you might have to refresh some of your memories to come back up with that. But there is a little discussion in the textbook, so make sure to read that. But again, this was something covered in Chem 3A, so I'm not going to spend a lot of time on it. Carbon with 4 groups is again tetrahedral. So the bond angle is 109.5. And when they're all bonding pairs, then the name is just tetrahedral. Now for our last structure here, we've got 3 groups. 1, 2, 3. 3 groups is called trigonal planar. Now with trigonal planar, those are 120 degrees separation. And in the particular case where they're all bonding pairs, it is also called trigonal planar. But there are trigonal pyramidals, there are bents, there are, what's the other one? Well, I guess trigonal pyramidal and bent are the only ones that I'm not showing. Oh, well, bent is shown here, but not for a trigonal planar. There's trigonal planar bent, there's tetrahedral, trigonal pyramidal. If that is confusing your head, then you need to go back and read that. If you remember vaguely what I'm talking about, then you're kind of in a little better position. Okay, so that is roughly what we're talking about when we say representing organic compounds as Lewis structures, and in terms of talking about the Sepper model that's identifying the bond angles and the geometries. Now, let's talk about some functional groups. Functional groups are an atom or a group of atoms within a molecule that shows a characteristic set of predictable physical and chemical properties. So functional groups are important because they undergo the same types of chemical reactions no matter what organic molecule they are found in. And so to a large measure, they determine the chemical and physical properties of a molecule. And they are the units by which we actually divide our compounds into families. So the families I've got listed here, and they're different by their functional group. Okay. And so these functional groups provide a basis on which we derive the names even for our organic compounds. And so we're going to go through some of these slowly. There is more than are listed here, just to kind of throw that out there. Let's see, alcohol, we don't have halogen listed. All of the functional groups that are related to just carbon compounds like alkene, alkyne, those aren't shown. Aromatics aren't shown here. Let's see, alcohol, amine, aldehyde, ketone, carboxylic acid, ester. Ethers aren't on here. Amides aren't on here. Thiols aren't on here. Okay, but just to give you an idea, there are lots of functional groups. Now we're going to learn them, and we're going to see how they relate to biochemistry when we get to the second half of this course. Now, a compound that contains an OH group is an alcohol. And so because it has an alcohol functional group, the names often have alcohol names in them. And so we're going to spend a little bit of time on each of the functional groups as we go through the chapters, learning how to name them, learning how to draw them. Now, your task in Chapter 1 is going to be learning how to identify them. So you need to memorize which functional groups are going to be present in which compounds, or vice versa. You need to memorize when you see a C double bond O with an H on it, that's an aldehyde. Okay? Um, all right, so just to give you an idea, let's look at some alcohols real quick. Here's an alcohol. Now, alcohols contain a hydroxyl. A hydroxyl is this OH part. And hydroxyl groups bonded to a tetrahedral carbon atom, such as in this example of ethanol, um, can be shown like this. So, where is ethanol? Ethanol is right here. So, we've got the condensed formula, which I didn't go over. Condensed just shows the way they're connected. Actually, it doesn't show the way they're connected. It shows groupings, but it doesn't show all the connections. So we're supposed to remember that CH3 is contained here in a C with 3 H's on it. Now, we're not writing and drawing chemicals yet. We'll get that in chapter 11, the next chapter, alkanes. But that's the difference between these two styles of formula. Now, the functional group part is just the OH part attached to this tetrahedral carbon. And remember, tetrahedral carbons are the way that we're going to see our carbons. Our carbons are always going to have 4 bonds on them, or 4 groups. They won't always be tetrahedral, but they will always have 4 groups. And just to kind of show you what I mean, we could have, actually it wouldn't be an alcohol. Yeah, what I was going to say is that we could have a carbon that has an OH on it that's also bonded to, triple bonded to something else. I suppose we could have something like this, but we probably wouldn't call this an alcohol. So I'm kind of contradicting myself a little bit here, but this is because I'm overthinking the definition. I forget this is, I teach Chem 150 also, which is biochem, and we go a little more in depth, so I need to back up a little bit. Okay, so an alcohol basically for us contains a hydroxyl group, an OH group. Now, there are some classifications. It could be primary if it is attached to a carbon that only has one other carbon attached to it. So here's the hydroxyl in all 3 of these alcohols. Now, the difference is that the carbon it's attached to, there's 2 ways to think about it. If it's got 2 H's, it's a primary. If it's only got 1 H, it's a secondary. And if it's got no H's, meaning the carbon doesn't have any lone hydrogens attached to it, then it's a tertiary alcohol. Another way to think of it, though, is how many other carbons are there. So this oxygen is attached to this carbon, which has another carbon on it. So it's primary. This one has 2 other carbons, so it's secondary. This carbon has 3 other carbons directly attached to it, so it's tertiary. Okay? Let's try a problem. Let's draw the Lewis structure and the condensed structural formula for 2 alcohols that have the molecular formula C3H8O. So, if you're struggling, I recommend just putting your carbons in a row. So here's our 1, here's our second. C3. Now, there's only 1 O. So in my first one, I'm going to stick my O on the end, and in my second one, I'm going to stick my O in the middle. And I can't stick it on the other end, or else it would just be the first molecule, flipped around. Now we can stick some hydrogens on here. 1, 2, 3, 4, 5, 6, 7, 8. And we have our first alcohol. 1, 2, 3, 4, 5, 6, 7, 8. So these are the Lewis structures. Now the condensed structures would be CH3, CH3, CH2, OH. And it's easy to know how many carbons are there if you drew it out. This one would be CH3, CH, CH3, and we would draw the OH. Now you could go up or down on that. I just went down to leave more room, but it doesn't really match. You could put it up. Either way. So that would be how you would do these. Now I could then ask you to tell me the bond angle on something like this, right? I have to tell you which atom to look at, but we could do something like that. Okay, let's see. What's going on here? Oh. iPad looked like it was stuck. Okay, let's go to means real quick. This isn't a mean. So amines, or amines, I don't know how you want to say that. I say it amines. Amines are compounds that contain an amino group. An amino is an NH2, or it's an, so which could be shown, so like when we say like a dash with an NH2 on it, it could be, we often use R to substitute like the rest of the molecule. So it could be an R NH2, but it could also be R2NH, and this is a secondary amine, and then it could also be R3N. So really it's a nitrogen containing compound. Often an amino group is an NH, but anytime we have these nitrogens inside a compound, depending on how many H's they have, that'll determine if it's a primary, secondary, or tertiary. As long as it's a nitrogen connected to a carbon, then it's an amine. So what we have here is methylamine. This is a nitrogen, an NH2 that's attached to a CH3. Here's the NH2 group. You can see that as we start to substitute these hydrogens with carbons, we get our other amines. So our primary amine simply has 2 hydrogens and only 1 carbon on it. But our secondary amine, we can replace one of those hydrogen positions with another carbon molecule. This one is just a methyl, meaning it's just a single carbon with hydrogens on it, but it could be a chain of carbons. In either case, this would become a secondary amine because the nitrogen now only has 1 hydrogen left, or because it has 2 carbons on it. And then that same nitrogen can be covalently bonded to 3 carbons. It still has a lone pair on it, but this is now a tertiary amine. That's how you say this. Primary, secondary, tertiary. So these are our amines, and notice that the amines also have the name amine in them. When we get to the amine chapter, we'll do some work naming these. Let's draw a condensed structural formula for the 2 primary amines with the molecular formula C3H9N. Now they have to tell us primary here because they don't want us sticking too many carbons on these nitrogens. So I'm going to do the same thing I did before, C, 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 and we're going to just stick our nitrogens on different positions here. On one of them, I'm going to put my nitrogen here, and on the other, I'll put it there. Okay, so now we need hydrogens. So I know that these are primary amines, so they're both still going to have 2 H's on the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then again, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Draw condensed structural formulas. My bad. They wanted condensed, so that would have been CH3, CH2, CH2, NH2. And this one would have been CH3, CH, CH3 with a NH2 on it. Okay. We're just looking at the top 6 right now, but there are more. We will go through more when we do our big chapters. So these are aldehydes and ketones really quickly. Now aldehydes have a C double bond O with an H on the end, and ketones are C double bond O's that are sandwiched in between other carbons. There's no H attached to one of those. I'm sorry, there's no H attached to the C double bond O. So that's going to be the difference. Now, in formaldehyde, which is the simplest, I don't have I don't have a picture of formaldehyde. The formaldehyde would be this H, C double bond O. Then you actually have two H's attached to the central carbon there. That's the simplest aldehyde. But they, as you start to add, as this gets bigger, then these become carbon molecules or carbon chains, right? I think this is just this guy right here, CH3, CH3. And then they get longer. Now, ketones, though, are always centered in between two carbons, and so the simplest ketone you can get is acetone, because it has to, by definition, have two other carbons on it, and so that's as small as it gets. If we put an H for one of these carbons, it becomes an aldehyde again. Let's draw an aldehyde or ketone here. Draw condensed structural formula for two aldehydes with the molecular formula C4H8O. Now, since they're aldehydes, we know that the carbon double bond O is going to have an H on the end. And so that already sort of tells us how our two structures are going to go. Now, I'm not sure if we can actually get two. Let's see. Let's see if we can get two here. Now, one of them is going to be just attaching the other carbons to the sides, like this. 4 carbons. We've got our O. We've got to put 7 H's. 1, 2, 3, 4, 5, 6, 7. Sorry, condensed structural formula. Now, C double bond O with an H can be shown as CHO, but I really don't like that. I like to show the C double bond O. Okay. Now, for our other one, we still know it's C double bond O with an H on the end. But now it's how we connect these that's going to make the difference. We can't just put the 3 carbons in a row, because that's going to be the same one as we had before. So we're going to have to get creative. So maybe we have CH3, CH, and then coming off of here, another CH3. Let's draw it out just so that you can visualize that works. So 4 carbons, 1 oxygen, 1 H, 2 H, 3, 4, 5, 6, 7, 8. So we got the right formula. We drew aldehydes both times because they have C double bond O's with H's, and that's how we know they're not the ketone version. You can draw a ketone with the same formula. Okay. These are carboxylic acids. You're used to regular acids and bases. Acids have H's on them that fall off, right? These H's don't tend to fall off. So this is a carboxylic acid. I'm sorry. These H's do fall off. That's, of course, what an acid is. This is it right here. That's the acidic H. Now, these don't fall off of oxyanions or off of binary compounds. These are what we call carboxylic because they are on a C double bond O. And this C double bond O with this OH on it is the carboxylate group, or the carboxylic acid part. When the H is gone, we call it carboxylate because it'll have, the H will be missing and there's going to be a negative charge here. And that's the carboxylate. So carboxylate and carboxylic acid are only different from each other when there's an H or when there's not an H. But the functional group of a carboxylic acid is the C double bond O connected to an O connected to an H. Okay? And lots of compounds have this in them, especially found in fruit and veg. So like tartaric acid and acetic acid and citric acid and benzoic acid and all of these different acids that you would see on your food labels, they are all going to be carboxylic acids. Now, these are not as strong as your acids and bases from inorganic chemistry. These are what we would call weak acids, but they are still acidic. Let's do an example. Draw a condensed structural formula for the single carboxylic acid with the molecular formula C3H6O2. Okay, so O2 we already know has to be part of the C double bond O OH. That's the carboxylate or carboxylic acid functional group. Now we've already got rid of that and one of those hydrogens, so now we just need to put two other carbons. Now there's no other place to put a carbon except right there, and no other place to put another carbon except right there. So we're going to end up with CH3, CH2, C double bond O, OH. So this is the formula. Now, sometimes this is shown as CH3, CH2, right, this stuff, COOH. Remember, aldehydes, which are this, are sometimes shown as COH. Oh, no, CHO. Wait, am I right? Is it COH? It's CHO. Sometimes they're shown as CHO. COOH is carboxylic acid. Okay. Now, there is one other that we're going to look at in Chapter 1 here. This is a carboxylic ester. Now, an ester is like an ether, and I kind of want to talk about an ether real quick. So an ether is when we have an O centered between two carbons. Now, that's an ether. When we kind of mix an ether and a carboxylic acid together, we get an ester. And so it's ether-like in that the O here has to be centered in between these two carbons, but it's carboxylic-like because it's the C double bond O that we would have in our acid. So when we see all of this together, C double bond O connected to an O that's connected to another carbon, this is an ester. These guys are responsible for those really nice smells that we get with like grapes and pineapples and fruits in general. Esters are often the molecules that have really nice fruity smells. Okay, now I don't have an example of or a problem to do regarding an ester here. But let me look real quick to see if there's anything else I can add, because this is the end of the slide, essentially, or the PowerPoint, essentially. Now I'm looking at your textbook, looking in the back of the book at the questions to see if if there's anything in here that you shouldn't worry about. I recommend doing at least one of each of these problems. So, like for example. I'm looking at on page 318 for chapter 10. It says section 10.4, what is a functional group? And there gives you like one or two, or actually there's like 5 or 6 different questions all about functional groups. Just answer, one or two of them. Go through, spend the time. It says there are 3 amines with the molecular formula C3H6N. True or false? That means you're going to have to try to make 3 amines with that formula and then answer true or false. It's a good exercise. Or complete the following structural formulas by adding enough hydrogens to complete the tetravalent. So they give you a bunch of skeleton structures and ask you to fill in the hydrogens. That makes you pay attention to how many bonds each atom has. It's worth doing. But what I'm looking at here is trying to see if there was anything else. Draw the structural formula for each of the following. The 4 primary alcohols with the molecular formula C5H12O. See, that's a good example. There's a part in here that asks about polarity. It asks, it's called looking ahead. So there's some parts on here that have you looking ahead, which is always good. You want to be reading ahead too. But let me just kind of briefly talk about polarity. So when we were doing Lewis structures, let me give you a couple Lewis structures. Let's do water. Let's do carbon. Let's do chloroform. So chloroform, I believe, is CHCl3, and then we'll just do CH4. Now, to tell if something is polar, a molecule, there's two things you have to look at. First, you have to look at the bonds, and you have to decide if the bonds are polar. And so this has to do with electronegativity. This has to do with the question 10.47 on chapter 10. It's asking you which bonds are polar. You'll need to look at a periodic table. Now, I will upload a periodic table that has electronegativity numbers on it for you, but if you don't remember this, go back to chapter or Chem 3A. In fact, the book that I've uploaded for you has 9 chapters in the beginning of it that are all Gen Chem. You should be able to go and look up the electronegativity bit. But what you're doing is comparing the electronegativity between the two atoms. If it is between 0 and zero point 0.4, we call this nonpolar. If it is between 0.4 and 2, then it is polar. And if it is greater than 2 in terms of the difference between the electronegativity of these numbers, then we say that that is an ionic bond and it is not a covalent bond at all. So when you compare these bonds, you end up seeing that the electronegativity numbers, I think oxygen is like 3.5 and hydrogen is like 2.1. So that's bigger than nonpolar. So this is a polar bond. So we can draw an arrow towards the negative side. And I always like to cross the positive side. So this means this molecule, this water molecule, has a negative side and a positive side, kind of like a magnet. Now I know that because the shape of this molecule isn't one that cancels out these charges. To give you an example, we also have a polar bond with carbon dioxide. Carbon is 2.4, oxygen's 3.5. That still fits right into the polar category. The arrow goes this direction, towards the negative side. But there's also a bond in this direction, towards this negative side. And so since carbon is right in the middle between two atoms that are trying to pull its electrons away, there's actually no pull at all. They cancel each other out, and this guy ends up being non-polar, even though it has polar bonds. Water has polar bonds, but they don't cancel out because of the shape, the bent shape, and so it's a polar molecule. Carbon here has non-polar bonds in all of these directions with hydrogen. So if they're non-polar bonds, then it's a non-polar molecule. In this case, these are polar bonds. If they were all polar bonds with Cl, if this was chlorine, and they were all polar bonds in all of these directions, then they would all cancel out, and this would be a non-polar molecule, because all of the different polarities would cancel. Think of it as what's happening down here. The electrons that are sitting right here and right here don't actually move this way because they're also being pulled this way at the same time. So nothing happens here. The electrons on carbon stay on carbon. But if we were to remove this as a chlorine, and let's say make it a hydrogen again, well now this wouldn't be a polar bond anymore. All of these others would still be polar bonds. This is still polar, still polar, still polar. This one wouldn't be polar, and so the effect would be we would have a whole side of this molecule that's negative and part of the molecule that's positive, because the electrons hanging out right here in this bond are going to migrate this direction, being pulled by the more electronegative atoms. So that's what it means to be polar or nonpolar. And again, this is important when you are deciding what compounds will mix. Polar compounds like other polar compounds, nonpolar likes nonpolar, but also for picking bond angles and for what's the other reason that we want to do this? Well, mainly it's just so that you guys have a better sense of what polar is. You need to be able to look at a molecule and tell if it's going to be polar or nonpolar. That is an important trait to be able to accomplish in this class. All right, guys, that does it for chapter 10, our first chapter. In the next chapter, we're going to take a look at alkanes. So I will see you guys in that video. All right, take care.